Thank you, Rob. Hope everyone can hear me well. As Rob mentioned, I work for ANSYS, and for those who aren't familiar with ANSYS, we develop, support and sell engineering simulation software, of which CFD is a part. And the topic of this presentation, covering Adjoint methods, focuses on one particular area of our CFD portfolio. Now, Adjoint methods, as an introduction, aren't a new technology. Development of adjoint technology has been going on for over 100 years, but what is relatively new is the implementation of adjoint methods into existing commercial CFD codes. And that's something that's only been made available within the last few years, really, and come to fruition. So that's really the essence of what I'm going to be discussing here. There was some mention in previous presentations about the importance of developing CFD methods and optimization, and the adjoint solver really lends itself well to those types of investigations. Okay, so let's move on. So I'm going to be talking about the introduction and motivations of development of an adjoint solver hooked into an existing commercial CFD code, an overview of the solver that's been implemented. I'm going to then go through a couple of examples to demonstrate the benefits of using this type of or adjoint technology. I'm going to start with talking about a NACA 0012 airfoil on a 2D example, and that will include a deterministic and uncertainty-based approach. And I'll then progress on to a 3D geometry and using the adjoint capability. And that will also include something called multi-objective optimization as well, which we'll show at the end of the presentation. So the objectives of the presentation here and of the current work that's being presented is to perform optimization under uncertainty using the sensitivities which have been derived from an adjoint simulation. And that's been implemented in, as I mentioned, a commercially available CFD solver, in this case Fluent. We're going to take advantage of the solver capabilities to explore designs which were potentially, a priori, were non-intuitive, i.e. those which you couldn't easily predict in advance of the simulation. And we can use the adjoint sensitivities which are derived to drive mesh morphing techniques as well. And this is a method to modify the mesh in order to attempt to optimize the geometry for a particular function. We'll then prove the effectiveness of a multi-objective approach as well in optimization. So we'll look at multiple objectives that might be practically more, it might be more practically appropriate to assign multiple objectives rather than a single objective for a sensitivity analysis. So I'll go through some of the basics of an adjoint solver. For some of you may be familiar, some of you not so familiar with an adjoint solver. But typically, as far as a CFD process, here we have in the middle, this is our flow solver. On the left-hand side, we have all of our inputs into our particular solver. We would have all our the boundary mesh, i.e. the surface mesh. We'd have the interior mesh or volume mesh. We'd have all the things like material properties, boundary conditions, things like this. They would all be used collectively to make up the boundary, to make up the input into the problem. And they're fed into the flow solver. And then, of course, out of the flow solver, we have all of these types of outputs: lift, drag data, plot data, all that type of information. But really, what we want to do is we want to understand how changes to the inputs are related to specific changes in the outputs. Okay? So we look at the problem in a reverse manner, and we say to ourselves, well, what do we need to do if we're interested only in drag? What do we need to do to all of these particular inputs to effect a change in the drag? How important are all of these different conditions on this particular variable on the output side? And this is where the adjoint solver comes in, because we can solve an adjoint solution by looking at a specific output variable, output parameter or observable, and look at the effect that's required on the inputs in order to effect that change in the output. So the adjoint solver provides a solution to this problem. So in a nutshell, if we consider that geometry and definition of the geometry is an input into the CFD solution, then we can say that, in a nutshell, it can tell you from a single run how you should change your geometry in order to improve it for a particular observable. Okay? So the adjoint solver can be used to compute the derivatives of an engineering quantity, which could be lift or drag, the observable that's defined, with respect to all of the inputs for the system. And the derivatives and sensitivities can be used to provide a very valuable input for the aerodynamicist, for the design engineer, in order to understand how to modify the geometry in order to improve it for that particular observable. So it'll allow you to provide not just the insight, but optimize the performance, and also detect areas where, for example, discretization errors may occur, things like this as well. So once the adjoint solution is computed, it can be used to guide an intelligent design in order to improve the geometry. So here there's a very simple case with vectors which are displayed on the geometry, indicating to the user how the geometry ought to be changed in order to improve it, for example, to reduce drag, etc. Okay, so a slide of some maths, but we won't go into too much detail. As I say, these solvers have been developed over an extended period of time, so we won't go into too much detail on this, but just to give you a flavour of how the solver works. If we look at our quantity of interest, which is our J value here, and that is, there's a relevance on the quantity of interest from the flow solution and the inputs into the problem. Similarly, from a CFD Navier-Stokes solution, we'll have the residuals, which equate ideally to a zero value. So we can use this information in order to determine or expand them out based on a change in the inputs. So if we apply a change in the inputs on the up here on the change of quantity of interest, the J value, we can see that there's an effect here in terms of the change on the inputs here. And similarly, we can also apply on the residual side down here through a process of linearizing Navier-Stokes equations. Now, we can equate these or bring these two initial terms together in order to bring them together. And that's done with an additional term and something called Lagrangian multipliers in order to derive an adjoint equation. So ultimately, what we're left with is a characteristic equation here which relates the change in the quantity of interest, i.e. drag, to change in particular inputs. And this is the heart of the adjoint solver which has been implemented. And it bears a lot of resemblance to the standard CFD solver characteristics in terms of the fact that it uses an AMG multi-grid solver. We have similar access to things like current numbers under relaxation factors as you would normally do with a flow solver. We have an iterative process, and we have residuals to be able to monitor during the solving process. And the current implementation requires roughly the same effort in terms of the resources required to run it as a standard conventional flow simulation. So if we use this particular solver and run through an example case of how it's applied, we converge the adjoint solution for a chosen observable, for example drag. Bear in mind that the CFD solution has been calculated prior to this adjoint solution, and the data from that CFD solution is an input into the adjoint solution. So we converge the adjoint solution for that chosen observable, choose a control volume that encloses in this case the upper part of the rear vehicle. We can see this blue box around the rear of the vehicle in an attempt to reduce drag on the vehicle. We select which surfaces within the volume are allowed to move, so there's some control over constraints, what can move, what can't move within the control volume. And we can use the shape-sensitive information that comes out of the adjoint solution in order to intelligently drive modifications to the geometry. So here we can see some vectors where we're amplifying, it's basically an amplification factor on the vectors. But the colouring is showing the direction of suggested modification in order to reduce the drag, and the vectors are showing the magnitude of that, the magnitude and the direction as well. So we can see here through the amplification factors how we're moving the design, or the design changes being suggested by the adjoint solution. So now we move to our NACA profile, and we're going to first look at the deterministic approach, i.e. Neglecting the effects of uncertainty. And here's the process on the left-hand side. We start at the top with the baseline configuration. Just like with the example car case I showed, we have a control volume definition which goes completely around the airfoil case, this NACA 0012 case. We go through the CFD convergence, the adjoint convergence, and then we can also apply the sensitivities which are derived from the shape sensitivity data from the Adjoint solution and apply those to a morpher in order to morph the surface as well. And we can loop round in this process in order to optimize the design for specific inlet conditions. In this case, we have fixed inlet velocity and a fixed angle of attack. So here's the converse CFD solution. You can see the original profile for the NACA profile. And we can see the residuals for the adjoint variables, which come down, similar to we would see in a normal CFD simulation. And here we can see the propagation of the adjoint sensitivities onto the surface mesh in order to be able to move or morph the nodes on the boundary. We have a series of control points which are assigned here with these little blue points here, which are assigned within the control box. And the morphing is guided by Bernstein polynomials, which are spline fits between each of these control points. And it controls and smooths the level of morphing of the nodes around the surfaces. Okay, so here in this movie we can see what we're doing is we're looping through this process. We're starting with the original design and we're optimizing it to increase lift over drag ratio. Okay, and we could just take lift, we could just take drag, but we can actually take a ratio as well as a single value. So we're starting at 12, we're moving to over 50 in terms of the lift drag ratio. And we're allowing it to automatically go through this process of solving and morphing in the background. And you can see on the bottom right here, we've gone through over 100 optimization steps or design points. And we can see the L over D ratio is gradually increasing up to this value over 50. Okay. Okay, so now we've looked at a deterministic approach where we've got fixed input conditions. Now we're going to look at something where we have a profile, because in reality, obviously, there'll be it could be a particular profile of or density function associated with input variables. Of course, you can imagine, for example, for an aircraft flight cycle, it'd see a whole range of different attack angles during flight. So what we can do is, rather than having a fixed one, we can start to look at a variation. And there are different ways in which we can look at the different variations. There are a number of them stated down here. We can look at a mean value optimization, a variance optimization, a mean value penalty optimization. There are various different approaches that we've looked at, and we've progressed in the simulations with highlighting on three particular ones: a mean, a variance, and a mean value penalty as well. And you'll see those in the next slides. So we started here by looking at the particular attack angle or the variation in attack angle, and taking what's called a Latin hypercube sampling procedure in order to sample out particular points in order to realistically define that definition for the parameter. And here we have all the different attack angles that have been analysed for this particular case, from alpha 1, alpha 2 up to alpha n. In this case, I think we took 20 particular angles of attack, which represented the sample points. And for each point, as we go down the tree, we solve the adjoint solution as we move down. So here for the mean value optimization, we can see the sort of ranges of lift to drag ratio that have been produced, starting at 12 and moving up to over 50 with the MVO approach. Using the variance optimization, we can see on the right here that we've significantly reduced the variation. And you can also see that in the pressure plots as well. And there's a little variation in the geometry using a variance optimization approach. But really what we want to do is we want to maximize lift over drag and also minimize the variation, because we want it to be able to consider all of the different potential variations in the parameters. So then we've taken an approach of using the mean minus 3 times standard deviation. So what we're trying to do again here is we're trying to maximize the lift drag ratio, but also minimize the variance. And you can see we do have some variations in the pressure contours across the cases. So if we combine the cases, we can see here what we've done is, in this network system here, we've combined all the different approaches of the deterministic approach, the variance, mean value penalty, etc., and combined them with an optimizer down here, which is this part onto the network system down here. Our inputs are the angle of attack and lift drag ratio as the output. And then down here we can see some of the output that we've derived. So here we can see the density function for the original NACA 12 profile. And what we want to do is we want to push that over to the right by optimizing the design. So we can see all of the outputs on here, which are the blue, the red, the green and the purple. relevant to the deterministic approach, mean value variance and mean value penalty. So what we're trying to do is we're trying to push all of these L over D values to the right, but also maintain, and minimize the variance. So we can see these ones are still quite peaky. We still have quite a high peak. We're trying to reduce that, particularly this one, the green one, with the variance approach. But we decided that this one with the mean value penalty was an optimum approach which pushes all the values in terms of the mean values over to the right-hand side to increase the lift-drag ratio, but also the variance is also relatively small as well. So we can see some values here in terms of the mean values from 12 up to, with the mean value over 50 here, and also the variances drop from 184 down to 8.8. So we have a significant drop in the variance as well. So the MVPO seems a good compromise to maximise the mean and minimise the variance for the knuckle profile. Okay, so now we've applied that to a 2D example, and we're going to apply that onto something a bit more realistic with a bit more realistic boundary conditions and variability on input parameters. So we have this simple Formula One front wing, front end geometry, and the goal here is to increase the downforce to drag ratio. And we can run a standard flow calculation to obtain the baseline flow field, and then run the adjoint solver to obtain the increase the downforce and reduce drag. We can see here the vectors placed on it as we progressively increase go through the amplitudes. So the process is similar. We solve the CFD analysis on the front wing. We run the adjoint solver. We look at the adjoint sensitivities. This provides us with a local optimum, and then we can use that information in order to progress through the morphing stage. And we progress from local optimums to a global optimum across the design space. So here what we can see is that process visually. We're starting on the bottom left here, we're starting from a downforce to drag ratio around 3.35, and we're allowing the adjoint solution to automatically modify and morph the front wing and end plates in order to improve the downforce to drag ratio, and you can see the design points that it's running through as it progresses. Okay, the changes in the geometry are very minor. Okay, so here we can see the baseline geometry and the modified optimized geometry for that particular, to compare the two. As I say, the geometry changes are very small. Okay, so with smart optimization, the result of the optimization reveals a change in the shape that would have been difficult to predict in advance. And it would also be difficult to characterize those changes in the geometry by creating geometric parameters in advance as well. So the changes in the geometry are very arbitrary across the geometry. So the adjoint solver determines the optimum design by analysing the current design and recommending an improved performance design based on the observable that's been selected. Now we can take that a step further and look at multiple conditions as well. Rather than just a single flow condition with single observables, we can also extend that with the adjoint to look at multiple observables and multiple flow conditions as well. So now we have an observable which is dependent on multiple conditions as well. And we can use those and take multiple sensitivity data sets and combine them together into a single output result. So we'll show that here. But essentially we have a base geometry and we have multiple conditions. And we can take the sensitivity data from each of these conditions simply by exporting the sensitivity data file and combining them into a single multiple conditions, or a case that considers multiple conditions. And that can be done by a weighted combination of all of the operating conditions that's visible by the geometry. So the goal then is to redesign the front wing to improve the downforce to drag ratio. In this case, we've done it for a particular track condition because that represents multiple variations on uncertainty in the input conditions, and also derive a general framework for any kind of deterministic attribute of the objective function that's selected. Okay, so the track now what we've actually done here in order to give us that variability on the input is to select a specific track. And what we've done is we've selected a Monza track here, and we've split the track up into a number of different segments. Within each segment, we've determined the variation potential in all of the steering angles and all of the velocity that's imparted onto the front wing assembly. And those are then defined as a density function for steering angle and also for the velocity magnitude. So we end up with this three-dimensional description of the track, which is the identity card of the track. And we can see how the steering angle and the velocity varies as the front wing would go around the track. Okay? And this will now represent an input into the adjoint simulation in order to look at a probabilistic output on improving the mean characteristics of downforce to drag ratio. So here what we've done, again, we've used a sampling process. Instead of Latin hypercube here, we have a larger number of points, and we've used a simplex stochastic collocation approach in this particular case. But the approach is still the same in terms of the sampling points that we use. We apply a morphing box, similar to that you would have on a legal box constraint on a front wing. It restricts the amount of movement within this particular zone. And we also define a number of control points, and this will also affect the available morphing as well. Here we've used a radial basis function morphing tool with a steering module, and it allows movement of the tyre geometry and also suspension arms as well, so we can take account of those modifications. And we can look, depending on the different sample points, we can look at the different characteristics that are produced from those particular cases. Okay, so I'll speed up a little bit. A particular output here that's visible is the contouring, where we can look at the adjoint solution here is telling us to push the geometry in or pull the geometry out in order to improve it. That's a particular sample point example taken. And the deformation around the control points can be seen here as the mu minus 3 sigma as the maximum deformation. So finalising this example case with the adjoint, we started with the baseline geometry shown on the left-hand side. We had this bimodal behaviour in terms of the density function on the output in terms of downforce to drag ratio. And then with the optimised design, primarily modifications are in these particular regions. We have this density function which is produced, which represents an improved modification for that particular track. And that was done using 10 sample points. But you can see here the increase in the mean downforce to drag ratio and the reduction in the variance. So here we can see the difference between the original design and the blue design, which is the optimised front wing for that particular track. And there's no reason why you couldn't use the same process on looking at different front wings for different tracks. So summarising then, an adjoint solver has been successfully implemented into commercial code. Deterministic and uncertainty-based approaches have been shown. A successful improvement of the wing has been obtained using this approach, and it's been demonstrated to drive the optimisation process even in the process of, even in the existence of uncertainties, and take account of uncertainties as well. Thank you.